Today we're going to talk about forces, and I want to talk about several different problems in forces. We'll go over some of the physics and the equations for different force problems with friction. So first we're going to start off with an object on a horizontal surface with an applied force, and our first step is to draw a free body diagram with labels. And then next, I'm going to just compare the two different problems. When I have force applied at an angle, I'm going to draw a free body diagram with the forces as they actually exist. First, keep in mind that force gravity on each object is equal to the mass of the object times the acceleration due to gravity. And then we'll keep going. What I'm going to need to do is take the force applied in the second drawing, and that force applied does not, it's not in either the x only or the y only direction, it's in both. So what I'm going to have to do is find the x component and the y component. And the y component is opposite the angle, so it will be FA sine theta. And FAX is adjacent, so it's going to be FA cosine theta. And now I'm going to redraw the free body diagram so all my forces are just in the x direction or the y direction. So what I can do from this in each of these pictures, I'm going to go back to my first free body diagram. And first I'm going to do the sum of the forces in the y direction. If I make up positive, force normal minus force gravity equals the mass of the object times the acceleration of the object, Newton's second law. And it's the acceleration in the y direction, which is 0. So we get force normal equals the mass of the object times the acceleration due to gravity. In the x direction, if we make FA positive and force friction negative, we're going to have FA minus force friction equals the mass times the acceleration in the x direction. Force friction is the coefficient of friction times force normal. And then I'm going to plug in force normal equals mg for force normal and divide both sides by m to solve for the acceleration. Keep in mind, if I wanted to solve for anything else, if I want to solve for the mass of the object, I could use this equation, solve for the mass of the object. If I wanted to solve for force applied, and I had coefficient of friction, mass, and acceleration, I could solve for force applied. I can even solve for the coefficient of friction. I'm just in the examples today going to solve for the acceleration in the x direction. The next object, the big difference is in the y direction, force normal and force applied are in the positive direction, force gravity is in the negative. So I get force normal minus force applied y, plus force applied y minus force gravity equals 0 because we're in equilibrium in the y direction. So force normal equals force gravity minus Fay. And keep in mind Fay is Fa sine theta. So force normal is mg minus Fay. Some of you are going to want to solve for force normal in this case and come up with a number. I can understand the desire to do that. But what we can lose when we solve early is we can lose that some things cancel out, a greater understanding of what's actually going on, things like that. So when you just start plugging in numbers, you tend to lose a better understanding of what's going on. The next thing, keep in mind that these two equations look incredibly similar because, sorry about that. Let me go back for a second. Those two equations look incredibly similar. And we just have the force applied here minus coefficient of friction times force normal cause the object to accelerate in the x direction. Here we have force applied in the x direction minus coefficient of friction times force normal causes the object's mass to accelerate in the x direction. So that's pretty much the entire concept right there. Then we can move on to our next page. When we're on a slope, we have an object on an incline, the first thing we're going to do is draw the forces that actually exist on it. Force normal is perpendicular to the surface, so force normal is up at an angle. Force friction is along the surface, so it's at an angle up the surface. Force gravity is down. The big difference in these problems is since acceleration will be along the surface, we're going to choose our x direction along the surface, our y direction where we're in equilibrium perpendicular to the surface, and so we're going to have to resolve force gravity into y, force gravity y, and force gravity x. And the angle of the slope is equal to the angle at the top of this triangle. This is a right triangle. So force gravity y equals Fg cosine theta because it's adjacent to the angle. Fgx is Fg sine theta. It's opposite the angle. So keep moving on. We can redraw our free body diagram, and we'll have force normal, force friction, force gravity y, and force gravity x. This is incredibly similar to the first problem on the last page. So we'll do the sum of the forces in the y direction to find force normal because we have force friction. If there weren't force friction, if there's no force friction, I don't really need force normal or the sum of the forces in the y direction. I use the sum of the forces in the y direction, so I have force normal, so I can calculate force friction. So when we look in the x direction, we have force gravity x minus force friction equals max. So we have force gravity x minus coefficient of friction times force normal equals max. Now I'm going to plug in, and one advantage of plugging in more stuff is you can see that the masses cancel out, which is kind of a cool result because it turns out that on a slope, the only thing that determines its movement or its acceleration down the slope is the coefficient of friction. The mass of the object actually doesn't matter at all, which is kind of nice. So now we've solved for the acceleration of the object. And we could even pull the acceleration due to gravity out of the equation and do g equal times sine theta minus mu cosine theta equals ax. That just simplifies the equation a little bit. Now I'm going to do the first Atwood problem. I'm going to draw two free body diagrams for each object. And keep in mind, I need to choose a positive direction so the front and the back of the car go in the same direction. That is, the entire object is moving in the same direction. So if I choose up for object 1, I've got to choose down for object 2. That's one of the biggest tricks of this problem of Atwood. The other is the two tensions are the same so long as the pulley is massless and frictionless. And then I can do the sum of the forces for the first object is Ft minus Fg1 equals m1a. For the second, it's Fg2 minus Ft equals m2a. Now the great thing is I can add the two equations together and Ft cancels out. And the nice thing here is we get a result that we see all the time in Atwood, which is the sum of the forces causes the entire mass of the system to accelerate. So solving this, I'm going to get the difference in the masses over the sum of the masses times the acceleration due to gravity is equal to the acceleration. And once again, I put this in a box because this equation is what you're looking for. It's the total force pulling the object forward minus all the forces pulling the object backwards cause the entire object, both masses, to accelerate. We'll see that in the next problem because, again, I'm going to draw two free body diagrams. I'm going to make this a slightly more complicated because I'm adding force friction. So this is slightly more complicated. Force friction exists. I'm going to choose the whole object travels in one direction as positive, so that's to the right for object 1 and down for object 2. If you have friction, we need to do the y direction for the first object to find force normal. And typically in Atwood, force normal equals mass 1 times g. And this is modified Atwood, actually. Sum of the forces on the first object in the x direction are Ft minus force friction equals ma. Sum of the forces on the second with down positive is Fg2 minus Ft equals m2a. That's Newton's second law. Once again, I can add the two equations together. Force tension cancels out. If there weren't friction, these equations would look identical, except there wouldn't be friction in the orange equation, and there wouldn't be friction right here or there. But if there is friction, we've got to account for it. Friction is the coefficient of friction times force normal. Keep in mind this looks like all the forces pulling the object forward minus all of the forces pulling it backwards cause the mass of the entire system to accelerate. It looks like Newton's second law for the whole object. And then we plug in mg, m1g for force normal. And when we solve, what we're going to get is a similar but slightly different equation than what we got on the last Atwood problem. All right, guys, I certainly hope this helps. This is pretty much what we didn't work on is objects that are pulled straight up and pulled straight down. But we did work on some of the force problems for all of the other type of objects for our force problems. And I hope this helps. Thank you very much.